Black holes are the most powerful prisons in the universe. Once you cross their boundary, escape is impossible. Yet these invisible giants are not silent. They warp space, rip apart stars, and create energy beams brighter than entire galaxies. The shocking part? We've actually seen their fingerprints. From the motions of nearby stars to cosmic ripples in space-time itself, scientists have devised ingenious ways to expose these hidden monsters. Today we break open the story of how humanity learned to see the unseeable. How do you study something that swallows all light? That question sits at the heart of black holes. By their very nature, they hide from us. Light goes in but never comes out, which means the usual tools of astronomy, telescopes, lenses, cameras, simply can't reveal them. It's as if the cosmos itself has built an object with a "do not look" sign painted across it. Scientists have faced many puzzles before, but few have been as stark as this. Here is an object that exerts an enormous pull on its surroundings, yet cannot be glimpsed directly. This paradox seems straightforward, but it pushes every scientific instinct to its edge. We rely on observation. The sun, planets, distant galaxies, all made visible because they emit or reflect light. Black holes reject that idea. They are places where light itself gets trapped. That leaves us with a fundamental problem. If you build your science around what can be seen, what do you do with something defined by its invisibility? The contrast is almost theatrical. Out at the edges of galaxies or in their cores, these monsters twist and stretch space, shred stars, and shape entire systems. They are among the most violent sources of power in nature, yet to the human eye, they are blank spots. This strange duality, objects that dominate without appearing, has always fascinated thinkers. Philosophers wonder what it means for reality to hide itself. Scientists see a challenge, the kind of riddle that forces us to invent new ways of learning. Imagine the situation like this. Picture yourself in a dark forest. Somewhere nearby, a predator moves. It makes no sound. You can't see its form, but you feel it. You sense the weight of its hidden presence, rustling the environment in the tiniest ways. That is what it is like to consider a black hole. You are aware of the force, you see effects in the surroundings, but not the source itself. Astronomy in the age before modern instruments had to work under conditions just like that, watching the forest without ever catching sight of what lived inside. This makes the scientific problem unusual. When we attempt to learn about a new type of particle or a new class of star, at least we can point instruments and expect signals to return. But black holes absorb almost every signal we could hope to receive. That gives them an aura unlike any other cosmic object. The gap between what they do and what we can see is so wide that some voices in science long wondered whether black holes were more myth than fact, mathematical curiosities instead of physical bodies. The early wrestling with these ideas tells us a lot. Without direct proof, people had to lean on thought experiments and theories. The questions weren't only scientific, they were also philosophical. If the laws of nature allowed such things to exist, what did that say about the knowable limits of the universe? If something of immense mass and density could hide inside a veil of darkness, maybe the act of knowing itself had boundaries. Black holes became a symbol both of physics at its most technical and of mystery at its most haunting. Without detection, though, such an object remains only speculation. You can write equations that suggest it. You can sketch models where gravity grows so intense that light cannot part from it. But until you can present an observation, you cannot be sure. For centuries, this doubt hung over the subject. Were people chasing shadows made of numbers or pointing toward real features of the cosmos waiting to be confirmed? The stakes were high. If black holes truly existed, they would rewrite our sense of how matter and space interact. They would anchor the behavior of galaxies. They would offer testing grounds for physics under extremes that no laboratory on Earth could hope to match. But if they turned out to be illusions of math, a correction would ripple through the structure of astrophysics built upon them. This was not a side project, it was a pivot point for the understanding of the universe. Here lies the heart of the fascination. You have something that both terrifies and compels. Its invisibility is not a weakness, it's the hook. Humans are drawn to what hides just out of sight. The idea that a thing could exist beyond all vision while holding enough energy to unmake stars is nearly irresistible. Black holes became monsters in our imagination, but not ordinary monsters. They were monsters you could not lay your eyes on. The strange philosophy of that invisibility extended beyond science, too. Some thinkers saw black holes as metaphors, gateways, symbols of what lies beyond perception. Others focused strictly on the astrophysics. In both cases, the same core fact gave them power. You cannot look at them directly. Unlike planets, they will never reveal themselves with reflected starlight. Unlike glowing stars, they will never blaze in the sky. They are absence made real. So a practical question followed. If your telescope cannot see them, how do you find them? You don't throw away the challenge or declare defeat. You look for clues. You ask whether such a monster truly leaves no trace. Could its pull on surrounding matter, or its indirect whispers, give it away? This is where imagination turns to engineering. Instead of waiting for light from a black hole itself, astronomers looked for the pieces of its environment that refused to obey ordinary rules. Slowly, the puzzle gave way to creativity. Scientists realized that what goes missing can say as much as what is seen. The way a star sways, the way gas circles, the sudden flicker of radiation, all of these might be hints. Just as a fish hidden beneath the surface of a lake can be inferred from waves on the water, so too a black hole could be noticed by the disturbances it caused in its region of space. It was a different philosophy of detection. Instead of trying to grasp the silent predator in the forest directly, you listened to broken twigs, watched shifting shadows, studied tracks in the soil. Nature doesn't erase all evidence, even when most of the evidence goes into the void. If you could map those smaller signs, you could build a case. And with patience, data, and better technology, suspicion could grow into certainty. This set the stage for some of the greatest leaps in modern astronomy. The invisible monster could be made visible, not by catching light from within, but by following how its gravity seized and reshaped the world around it. That was the moment when theory leaned closer to proof, and when the human method of persistence, observing the unobservable, began to break open the dark cages of the cosmos. The real breakthrough began with one simple line of reasoning. If black holes bend space so intensely, then the stars around them must dance to their silent tune. Following those motions would eventually reveal the presence of the unseen master hidden at the center. As it turned out, gravity itself would be the first trail of evidence. How do you see a black hole without ever laying eyes on it? At first, the question sounds impossible. By definition, these cosmic objects emit no light, no reflection, no signal that can travel directly to our instruments. But nature provides another path. You don't need to see the predator if you can watch how the forest animals move around it. The story of how scientists first made black holes visible begins in much the same way, by paying close attention to the stars in their neighborhood. When astronomers trained their telescopes on certain regions of the sky, they noticed peculiar behaviors. A star would trace a path that curved at angles too sharp to be explained by empty space. Some appeared to orbit in ellipses drawn around points of darkness. It was as if they were chained to massive companions that refused to glow. Watching a star pulled into a steady loop with nothing apparent at its center violated every expectation. Stars are bound to stars, planets to suns, moons to planets. Something invisible pulling with such authority seemed less like normal astronomy and more like a hint of missing matter of extraordinary density. In those skies, the orbital paths carried the first hints. Imagine standing on a hill, watching leaves circle downward into a pond. They spin round and round, yet you cannot see the water current that drives them. The clues lie in their motion, not in the thing pulling them. Astronomers recognize the same principle. The orbital loops of these stars could not be explained by thin air. Something compact and extraordinarily heavy had to lurk at the very center. A compelling example rose from a system where a visible star danced around nothing. Careful observations registered tiny shifts in wavelength from that star's light, evidence that it was moving rapidly back and forth, pulled hard by a dark partner. The size of the orbit and the sharpness of those velocity changes pointed to a body many times more massive than the Sun, yet showing none of the normal features of a star. The companion was no white dwarf or neutron star. The only explanation that fit was a black hole. This system, later named Cygnus X1, became the first convincing case for a true black hole beyond theoretical sketches. What made it persuasive was not what could be seen, but the absence that explained everything else. The star's orbit and the X-ray flashes detected from the region told a matching story. Gas spilling from the visible star was falling onto the invisible object, heating as it spiraled inward, producing high-energy radiation. The dark partner made itself known by its effects, by its gravitational fingerprints, even though no eye or camera could record its surface. The logic required patience. You cannot simply point out into space and claim a hole in the night is a black hole. Many dark patches exist for mundane reasons: dust, distance, faint stars. The key was the precise orbital behavior, the acceleration of the companion star, and the appearance of energy, bursts at the correct scale. Those pieces of evidence locked together into a single picture. Here was something that revealed itself only through its hold on visible matter. Think of it like this. If you saw a swing in a playground moving back and forth, even if the child on it was cloaked from view, you would conclude someone was there. The motion of the swing tells you a force acts upon it. The case for a black hole followed the same reasoning. A star's repeated dance, curved and sped up, spoke for the grip of an unseen mass. Once recognized, that principle could be applied across other systems. Where stars behaved as if pulled by nothing, astronomers suspected a black hole held them in orbit. With Cygnus X-1 as an anchor, black holes shifted from the realm of mathematical possibility into observable reality. What had lived in equations now had a real-world counterpart written into the sky. That transition changed the culture of astronomy. The skeptic's phrase, "only theory," gave way to cautious acceptance that black holes were as real as any star or planet. Once the first had been identified, the method spread. Astronomers scoured the heavens for stellar companions moving in similar odd orbits. Each new detection added another brick to the case. The irony is striking. Black holes are defined by their ability to hide information, yet they could be confirmed by their influence on others. The fact that astronomers could measure velocity shifts in a companion spectrum or chart slow arcs across the sky gave them a backdoor into a world sealed against direct light. These traces were not much different from seeing footprints pressed into soft ground. You may never glimpse the animal itself, but the tracks are undeniable. What made Cygnus X1 convincing was the match between prediction and observation. General relativity predicted compact masses could bend and hold stars in unusual orbits. Here was a star doing exactly what made Cygnus X1 convincing was the match between prediction and observation. General relativity predicted compact masses could bend and hold stars in unusual orbits. Here was a star doing exactly that. The presence of high-energy radiation from the system further confirmed gas was meeting an intense gravitational well. The evidence painted a consistent portrait. Nothing else in astronomy fit the bill. Over time, astronomers mapped ever more examples. Some found stars circling far faster than expected for the distance to their center. Others discovered systems where massive objects exerted control on entire groups of stars. Each new case tightened the understanding. By reading these orbital signatures, scientists could weigh the invisible. They could measure black holes not by sight, but by the rhythmic loops of their companions. The most striking examples came from dense galactic centers where stars whipped in loops around nothing visible at all. Their paths were too fast, too close to be caused by common masses. The only possible conclusion, the hidden presence of black holes far beyond stellar size. But even on the smaller scale with Cygnus X1, the lesson had already been learned. To see the unseeable, watch what it does to its neighbors. This indirect vision gave scientists tremendous power. They could chart where black holes resided, what masses they carried, and how they influenced surrounding space. They were not blind after all. In a universe ruled by gravity, you can follow the pulls and tugs to locate even the darkest engines. The invisible became trackable. One might expect such measurements to be crude, but the precision grew remarkable. Observatories could record tiny shifts in spectral lines, the faint red and blue badges of motion toward and away from Earth. From those shifts, orbital speeds could be disentangled. From orbital speeds, masses could be calculated. And from those masses, black holes could be declared. It was a chain of inference that transformed absence into certainty. The first confirmed black hole stood as a proof of concept. Cygnus X1 was not merely a discovery for its own sake. It was a demonstration that gravity itself leaves behind a written record, legible to anyone with the patience to piece it together. For the first time, astronomers had a reliable way to reveal a black hole's presence. They had learned to see through the invisible grip it held on something else. That moment widened the horizon. The black hole was no longer a phantom of theory. It became a participant in the cosmic stage, located and weighed, fixed in position by the orbit of its visible partner. An idea had become an object. A dark equation had become a system of stars and radiation that could be monitored and measured. Astronomy had carved a path to make the unseen real. The implications extended beyond that first case. With the detection method solid in hand, the search expanded. More candidates emerged, each tested against the same pattern. Orbital anomalies pointing to massive companions gone dark. Bit by bit, a population of black holes was revealed across the galaxy. What started as a philosophical question began to look like a census. The cosmos contained not just one invisible monster, but many, hiding behind the light of their partners, tugging silently. Seeing through gravitational fingerprints changed the way we describe them now. We do not rely on imagination alone. We can point to measured speeds, curvatures, X-ray fluxes. The monster became a measurable fact, not merely a symbol. It was no longer only about what black holes are. It was about the methods humanity built to pull them out of hiding. From then on, the invisible grip of black holes was no longer a mystery unsolved. It was a pathway to detection, a new kind of vision using orbit and force instead of light. We could finally see them for what they were, not through eyes, but through the stars caught in their sway. But gravity wasn't the only mark they left behind. Sometimes these dark engines revealed themselves more violently by igniting their surrounding matter until it flared hotter than the heart of a star. Where orbital evidence whispered, energy screamed. The next great clue would come not from motion, but from the storm of light generated before matter was swallowed forever. How can something invisible be the brightest engine in the universe? Black holes swallow light, yet the regions around them blaze with a fury no star can match. The paradox is striking. An object that emits no light of its own becomes marked out by some of the most intense radiation ever observed. The secret lies not inside the black hole, but at its edges, in the storm created when matter tries and fails to escape. Matter doesn't simply fall straight in. Gas, dust, or even entire stars get dragged into orbit, pulled into a spiraling path by the black hole's gravity. As this material whirls inward, it piles up, compresses, and grinds against itself. Friction heats it to astonishing temperatures. What you get is a feature called an accretion disk, a vast rotating structure of matter forced to shed energy as it gets closer to the event horizon. The contradiction sharpens here. At the core sits an object that allows no light to leave. Surrounding it, a disk glows hotter than the centers of stars. The more energy this matter loses, the faster it spins and the hotter it gets. By the time gas nears the boundary, its temperature soars to millions of degrees. At those extremes, atoms themselves are torn apart, and the radiation released comes out most strongly in the form of X-rays. So the darkest engines in the cosmos are surrounded by halos of invisible fire, detectable with the right instruments. You can picture it with a simple analogy. Imagine a piece of metal pressed to a grinder's wheel. Sparks burst from the surface, not because the wheel itself glows, but because energy is being shed violently at the point of contact. Around a black hole, matter plays that role. Gas collides and compresses, releasing energy in small, blinding flashes. To the human eye, these sparks would not show. The brightness lies outside ordinary light. But X-ray telescopes tuned to higher frequencies reveal the spectacle. When astronomers built such telescopes, whole populations of hidden objects came into view. What seemed like blank patches of sky suddenly lit up in high-energy bands. Some of these bright sources marked the locations of the most ravenous black holes, feeding actively on surrounding gas. They were not visible through ordinary optical telescopes, yet their presence shouted through these energetic bursts. One of the most striking insights is how the power grows as material spirals inward. The closer matter falls, the tighter the orbit, the greater the friction, and the brighter the flare. Each step inward ratchets up intensity. In the last moments before crossing the event horizon, energy release peaks. Material just outside the point of no return blazes so fiercely that it can momentarily outshine entire galaxies before vanishing from sight. Think about the irony. A trip toward destruction creates one of the most luminous displays in nature. Gas and dust fall into ultimate darkness, yet, on the way down, they become radiant. Falling into death produces light, visible across cosmic distances. This clash between annihilation and creation is what makes black holes centers of attention. They are both graves of matter and beacons of energy. Astronomers quickly realized that these signatures allowed them to go beyond indirect orbital evidence. They could map out black hole populations not just through how stars behaved, but also through how matter near the threshold burst into radiation. Accretion disks became identifiable markers. Where X-ray telescopes recorded flaring sources, a hungry black hole was the likely engine. In practice, scientists built catalogs of these cosmic furnaces. They noticed some flickered in cycles, others emitted steady beams, and a few launched jets of matter, stretching thousands of light years. Those jets carried particles ejected at near light speed, focused into narrow streams by magnetic fields. The radiation from the disks and the energy in the jets fed and shaped surrounding regions of galaxies. Each observation demonstrated a truth. A black hole's silence does not make it undetectable. Instead, its hunger leaves it marked out by violence all around it. If you cannot see the predator, look for the chaos it stirs. With new telescopes orbiting the Earth, astronomers began detecting these marks by the dozens, then hundreds. Where once uncertainty dominated, now data poured in. Each system revealed new levels of extreme physics in action. The beauty of the method was how consistent it became. The prediction said matter nearing a black hole must heat up, must radiate, and must peak in high-energy wavelengths. That is exactly what the instruments recorded. Observation met expectation at every point. Theory was tested not by seeing the black hole itself, but by monitoring its energy leaks, and the match held. If you could place yourself near such a system, the view would be terrifying. A swirl of matter tens of thousands of kilometers across, blaring with invisible radiation, jets of particles launched straight out of the poles, space around it twisted by gravity, time itself stretched. Yet even at that proximity, the black hole itself would give away nothing directly. The firestorm belongs entirely to the material doomed to be lost. As research advanced, astronomers discovered different feeding rates gave rise to different behaviors. Some black holes consumed matter at extraordinary speeds, their disks shining with near-constant intensity. Others starved briefly, then flared when unlucky stars wandered too close. This variability made them dynamic objects to watch, each system shifting between quiet and storm. High-energy telescopes even revealed systems at great distances, their signals crossing millions and billions of years before reaching Earth. These sources, called quasars, turned out to be powered by supermassive black holes at the hearts of young galaxies. Their overwhelming light comes not from stars, but from accretion disks burning with colossal intensity. In some cases, those quasars blaze brighter than the combined starlight of every sun in their host galaxy. This realization taught us that black holes were not fringe phenomena, but major players in cosmic history. Their ability to produce such dazzling outputs through accretion made them central energy engines in the growth and behavior of galaxies. In the end, an object designed to trap light revealed itself as one of the universe's most important sources of radiation, sculpting environments on colossal scales. The paradox holds a deep lesson about how science works. When direct vision fails, indirect markers become the path forward. We can know what lurks at the center not because we see it, but because we measure what happens around it. Light sacrificed on the way into darkness offers a final message, an obituary in the form of radiation. That message reaches us even though the source itself lies hidden forever. The closer we study, the more detailed this picture grows. Spectra of radiation from accretion disks reveal temperature distributions, disk structure, and sometimes even how fast a black hole spins. The pattern of flickers and bursts reflects not chaos, but laws of physics unfolding at their limit. By learning to read those signals, we map out properties of these invisible bodies. Science has built an entire toolkit from the glow of dying matter. To this day, no instrument can pierce the event horizon. Nothing crosses that barrier with information intact. But that boundary leaves no gap in our curiosity. Everything that leads up to it, each flash, each twist, speaks volumes. Black holes, silent at their core, become loud at their edges, yelling their existence through X-ray bursts across the cosmos. And so a contradiction turned into a method. An object supposedly invisible was made visible through the brilliance of its victims. Astronomers unlocked a new way of tracing black holes, using not light from them, but high-energy signatures of the matter they consume. Once again, persistence and engineering solved a riddle that at first looked unsolvable. But the journey doesn't end there. Light, or its absence, is only one sense we have built for our cosmic search. A deeper revolution was waiting, one that would open a completely different window, not through radiation at all. For the first time, the universe would be heard, as black holes betrayed themselves not by photons, but by ripples passing through the very fabric of space and time itself. Imagine hearing two invisible giants collide across the cosmos. For most of human history, space was something we saw with our eyes or captured with telescopes. We could measure light, look at orbits, even catch bursts of X-rays. But there was always another prediction sitting in the background waiting. A century ago, Einstein's equation suggested that space itself could ripple like water in a pond, not just the objects in that space, but the very fabric beneath them. It was a simple yet radical idea. Massive bodies in motion might stretch and squeeze the universe as they moved. At first, this was only a calculation written on paper. The concept sounded abstract, even speculative. To imagine space flexing feels impossible because we are used to it as the rigid stage on which events unfold. Yet relativity treated space and time as elastic. It said that if immense masses accelerated, they would push out waves of distortion, traveling at the speed of light. You could picture it like tossing a heavy stone into a still lake. Ripples spread outward, not in water, but in space-time itself. The beauty of the model was its clarity, but the challenge was enormous. These waves would be faint, passing through everything without leaving obvious signs. For decades, no one knew if we could ever detect them. The mathematics said they should be there, but a scientific fact does not feel complete until an experiment registers it. Astronomers wondered, could we ever be sensitive enough to measure space itself growing fractionally longer and shorter as a wave passed through the Earth? Mergers of black holes offered a natural test case. Take two objects each dozens of times more massive than the Sun, place them billions of light-years away, locked in orbit around each other. As they spiral closer, their motion disturbs the surrounding space-time so strongly that ripples expand outwards, sweeping across galaxies. When they finally collide and merge, the event releases more power for those brief seconds than all the stars in the visible universe combined. But unlike light, this power leaves in the form of gravitational waves, stretching and squeezing space as if the universe were one giant trampoline. This trampoline picture offers a way to think about it. If you press two weights into a fabric surface and set them spinning around each other, the cloth distorts. When they merge, the sudden shift thrusts out waves along the surface. The universe's version is far more subtle. The stretch and squeeze it delivers to Earth is smaller than the width of an atomic nucleus, an effect so tiny you might assume it could never be noticed. But physicists decided to try. They began to design machines able to track these vanishingly small length changes. The most ambitious was called LIGO, built to measure distance changes less than 1,000th the width of a proton. Its design seems almost simple in concept. A powerful laser beam is split in two, sent down two arms kilometers long, bounced back by mirrors, and then recombined. If a gravitational wave passes through, it stretches one arm while compressing the other. The returning light then shows a telltale pattern, revealing that space-time itself has warped in transit. Think of how careful you must be here. Environmental vibration, seismic activity, even the motion of cars on distant roads could drown out the signal. Engineers isolated mirrors, built giant vacuum tubes, used sophisticated feedback controls, and duplicated the detector in more than one site to reduce false positives. It was a build taking decades of commitment, testing science's patience as well as its creativity. For years, the machines listened, and nothing came. Decades passed with no detection at all. Doubts grew. Some scientists wondered if the concept was too ambitious. Perhaps the waves passed through Earth, but the sensitivity was still inadequate. Building detectors of such ridiculous precision without proof that they would ever work was a gamble. But the instruments improved, sensitivity climbed, noise was cut down. Each year the odds of success felt slightly better. Then, in 2015, everything changed. The signal lasted less than a second but carried clear structure, a rising chirp, a quick fade. What the detectors recorded was the final dance of two black holes as they merged. Billions of years ago, those immense bodies had spun together, collided, and fused into a larger black hole. Ripples from that collision traveled across the universe until they reached Earth. They passed through us invisibly, stretching and squeezing our planet ever so slightly. But LIGO was prepared. For the first time, humanity had confirmation. Gravitational waves were real, and black holes had announced themselves not with light, but with vibration across space-time. The value of this detection was more than symbolic. For the first time, we had heard the cosmos. Until then, astronomy relied entirely on light: visible, radio, infrared, ultraviolet, X-ray. Now we had opened a new sense. Like a person born with sight gaining hearing, humanity could access a different stream of information. The collision of black holes was silent to our eyes, but clear to our instruments. We had gained the ability to listen to the universe's darkest events. That first sound was only the beginning. Each new detection carried more detail. Different collisions had different masses, different orbits, producing waves of distinct signatures. By matching the signals to the equations of relativity, scientists could weigh the black holes, time their orbits, and sometimes even measure the spin of the final remnant. Information hidden from telescopes could now be drawn out by detectors tuned to stretches in space-time smaller than atoms. Gravitational wave astronomy now runs alongside traditional astronomy. Light continues to tell us much, especially about what happens before matter is lost to the event horizon. But gravitational waves tell us about the dark side, the interactions of bodies completely hidden from ordinary sight. For the first time, we can detect collisions of objects that release no light at all. Two black holes merging used to be the ultimate invisible event. Now it speaks directly to us, not with photons, but with distortions sweeping outward like sound waves in cosmic fabric. You might wonder what that ripple feels like. If you were floating in space as a gravitational wave passed, you wouldn't sense it. Your body would stretch and squeeze by tiny fractions beyond perception. Only precise instruments could note the shift. But that subtle change is enough to tell stories of cataclysms happening far beyond what we can see. They are events that can reshape entire galaxies, yet their fingerprint on our world is smaller than a strand of DNA. It is scale beyond intuition, enormous in source, minuscule in effect, yet utterly real. The importance runs deeper than confirming Einstein's century-old prediction. Every new detection tests relativity under circumstances never reproducible anywhere else. It probes gravity at its strongest, at the very edge of collapse. And because gravitational waves cross space almost unimpeded, they carry information about their source untouched by dust, gas, or scattering. They are messengers that travel clean across the universe, a pristine record of the collision that birthed them. With each improvement in sensitivity, detectors pick up more distant and smaller sources. What was once a theoretical hope has become a growing catalog of signals. We're now building a timeline of black hole unions scattered across billions of years, mapping events that would otherwise remain permanently unknown. It is the birth of a brand new branch of observation, as significant in its way as the invention of the telescope centuries ago. If you think of it as human perception, the balance is remarkable. Sight through telescopes let us watch the stars. Radio eyes allowed us to detect giant gas clouds and pulsars. X-ray and gamma-ray telescopes exposed the violent edges. But gravitational waves handed us hearing. With them, we are no longer deaf to the events locked in total darkness. We can eavesdrop on black holes crashing together in silence and yet echoing through space-time itself. For scientists, the implication is that nothing hidden remains beyond reach forever. Even events that give off no light leave their trace in another form. Building instruments that can sense beyond our normal range turns out to be the most powerful act of curiosity we can attempt. And when the payoff comes, it expands our contact with the universe in ways that radically change how we classify, map, and understand it. Of course, challenges remain. These detectors must filter thousands of false signals. They demand perfect alignments, careful construction, constant calibration. But each successful detection has validated the effort. Year by year, the catalog of mergers grows longer, and the black holes once imagined as silent monsters now create an audible record of their lives. Think of the transformation that has taken place. For centuries, black holes lingered as theoretical shadows. Then they became real through their pull on stars. Later, they revealed themselves in lightning-bright X-ray bursts. Finally, they spoke to us directly, not with light at all, but with tremors in the fabric of space-time. The journey has always been the same. Take what seems undetectable and find a way to detect it. By listening to the universe in this way, we are not just confirming ideas, but opening an entirely new domain of exploration. Each signal brings us closer to learning how often black holes merge, how massive they can become, and how galaxies evolve around them. We are recording the deep rhythms of the cosmos, vibrations so small they escape our senses, but so large they echo across creation. And yet, for all this triumph, one question lingers. We can hear them, yes, but what do these invisible giants actually look like when imaged directly? For centuries, black holes were mathematical ghosts. They lived only in equations, descriptions written on chalkboards, and in the notebooks of scientists. You could describe their properties, predict their influence, calculate their power, yet never place an image beside the theory. No matter how far telescopes advanced, a black hole's surface would not reveal itself. What you were left with was an idea, a boundary of no return and a center of infinite density, explored through imagination and confirmed through indirect effects. Then came the shift, the moment when humanity managed to turn the invisible into something you could finally see. We had at last a silhouette. The challenge was unlike anything astronomy had attempted before. A black hole does not emit light. Its hallmark is darkness. So the task was to aim for something darker than darkness and still expect an image in return. You cannot photograph the hole itself, only the shadow it casts against its brighter surroundings. Around a black hole, gas and light interact in unusual ways. Matter caught two close spirals inward, heating to enormous temperatures, glowing as it falls. Light bends back toward the object, some trapped in orbits by the intense curvature of space. Theoretically, all this should paint a ring of light around a void. The mission was to try to see that ring, but no single telescope could achieve the resolution required. The target lay millions of light years away. To detect a ring just tens of micro-arc seconds across would demand a lens the size of Earth itself. Building such an instrument physically was impossible, but researchers had another idea. Link telescopes across the globe, synchronize them with astonishing accuracy, and combine their data. In effect, the entire planet becomes the lens. Every observatory adds one more piece to the stitched-together mirror. The name given to this network captured the ambition, a horizon-spanning experiment. This was not simply pointing telescopes in one night and waiting for a signal. Every observatory generated enormous piles of raw data, disk drives filled with more information than could be sent over the internet. Data had to be flown physically across continents to central places where teams could process it. Algorithms checked timing to fractions of a nanosecond, aligning signals gathered across oceans. What followed were months of calculations, reconstructing the scattered information, into a coherent picture. Each step carried uncertainty. Any error in synchronization or calibration could produce a false feature. The world waited as the image was assembled, frame by frame. The target chosen was a black hole in a galaxy called M87, far larger than our own Milky Way. At its heart sits a giant whose mass dwarfs even Sagittarius, a star, the black hole at our galaxy's center. The reasoning was practical. A black hole that large, with a shadow immense compared to smaller cousins, gave the best chance of success. Its sheer size helped offset the distance. Even then, the scale was daunting. You were trying to resolve something as small as a pinhead set on the surface of the moon. Only by merging data from telescopes worldwide could astronomy reach that clarity. Finally, after countless checks and discussions, the result crystallized. Against the canvas of deep space, a ring of light took shape. A blurred, glowing circle surrounded a central void. The ring shone brighter on one side, dimmer on the other, twisted into an asymmetric halo. That tiny asymmetry was not noise, it was the imprint of matter moving at relativistic speeds, the side coming toward us, beaming more light than the side moving away. What the world saw for the first time was a black hole's shadow, cast against the bright whirl of its accretion. The image carried both simplicity and depth. To a casual eye, it was a fuzzy orange ring. To anyone who understood the journey, it was a revelation. Here, clustered photons traced their impossible orbits before succumbing. Here, space bent light back upon itself, curving trajectories as if the cosmos played with mirrors. The dark region did not show the interior. The black hole's true interior remains unseeable, but it marked the outline. This was the event horizon's portrait, drawn not in the language of math, but in the glow of captured light. If you picture what is happening there, it is remarkable. Photons, the particles of light that wander too close, are forced into looping paths. Some make tight turns and escape, some orbit multiple times before falling back. What escapes forms the ring we see. It is not an object itself, but the trace of light's last stand before collapse. In a sense, the image shows you two things at once: brutal darkness in the center and deflected light along the rim. For the first time, theory met sight. Equations written decades earlier had predicted exactly this: a dark circle surrounded by a sharp ring of emission. The glory of the result was not that it surprised scientists, but that it confirmed them. What had been thought experiments now existed as proof captured on a screen. The human eye could see what before only the mind could sketch. Black holes left mathematics behind and entered the gallery of photographed cosmic objects. The global effort also marked a turning point in collaboration. No single scientist, no single telescope could claim the result alone. It required observatories on opposite sides of Earth, data physically carried to common centers, and algorithms written by teams to decode the signals. It was an achievement made not by one nation or one scope, but by the planet acting as one camera. The Earth itself became the lens through which the image emerged. The image did more than satisfy curiosity. It provided numbers, measurements of mass, shape, spin. By comparing the size of the shadow to predictions, physicists could test general relativity under extreme conditions. The match was close. Einstein's framework once again held steady where space is most curved. But by repeating such observations, scientists hope to push the equations to their breaking point to find hints of new physics. The picture is not just an icon, it is a data set. For you as a viewer of that image, the meaning is broad. It proves that black holes are not simply metaphors or gaps in explanation. They are tangible features of the sky, photographable by instruments built on Earth. The silhouette of M87 star stands as a portrait of the unseeable. We can now point not only to numbers, but to a pattern of light, the first direct glimpse at what hides behind centuries of speculation. The appearance of that glowing ring captured public attention in a way few science results do. People saw it on screens, in newspapers, across social media. To many, it seemed strange, just a blurry circle. Yet it spoke of something profound. That blurry circle represented the edge of space turned in upon itself. It was not pixels alone. It was evidence that our species can overcome even the rule of invisibility imposed by a black hole. One could dwell on the symmetry of history. For centuries, black holes were thought experiments. Then they became indirect inferences, then data in high-energy spectra, then signals in gravitational waves. Finally, they became an image. The sequence of progress kept peeling back layers of hidden influence until nothing remained but the object itself. That image is the final proof of a journey across generations. If you were to stand, hypothetically, where M87 sits, the view would dwarf anything imaginable. Streams of matter pouring in, jets extending thousands of light years, photons looping and colliding at the brink. What we see on Earth is the compressed summary of those phenomena folded into one circle of brightness. Yet within that circle lies the story of matter, energy, and gravity operating at their most extreme. The technical method deserves its own moment. Very long baseline interferometry uses the timing of light waves captured at different observatories to reconstruct an image finer than any single telescope could create. In practice, it meant splitting beams, synchronizing atomic clocks across the globe, and weaving together signals gathered under different skies. The accuracy required would be comparable to aligning watches so precisely that they disagree by less than a billionth of a second. That alignment made it possible for faint whispers of radiation from the edge of the event horizon to combine into a coherent outline. Months later, when researchers announced the picture publicly, reactions ranged from awe to disbelief. Some expected sharper detail or more dramatic features, but what mattered was not crispness, but correctness. What you saw was the shadow, not the whole. Shadows by their nature are soft at the edges, gradual, imperfect. The fuzziness is part of the physical truth. It reflects how light is bent, scattered, and caught in unstable orbits. The picture, in its modest detail, was exactly the right achievement. With that success, a new era began. The same network that imaged M87 star turned to our galaxy's own center, chasing Sagittarius A star. That system created fresh challenges because matter there shifts rapidly, changing within minutes rather than staying steady over days. Combining such turbulent signals proved even harder, but again the method succeeded. Each new image adds confidence that the approach delivers real physics, not artifacts. The practical outcomes stretch into the future as well. Next-generation instruments aim to add more observatories, to increase resolution, to capture video rather than still frames. The dream is to watch accretion disks move in real time, to see light bend dynamically around black holes as if in slow motion. What begins as a single soft image will grow into a library of moving portraits, each tightening our grasp on what gravity does in its most intense regime. Through every lens, literal and metaphorical, the lesson stays the same. What was once theory is now sight. A black hole's shadow is no longer imagination, but evidence. You can see it, measure it, test it. Humanity looked at darkness and managed to draw out an outline. That outline confirmed the maps mathematics drew long ago. And this raises another layer of wonder. If a single image required turning the Earth into a telescope, what will it take to probe the physics buried deeper within? Black holes do not only resist observation, they challenge the very laws we apply to describe the cosmos. The next puzzle is not whether they exist, but whether our physics can contain what lies at their core. That is where the shadow we now see leads, to the breaking point between known science and mysteries still ahead. What happens when the known laws of physics break down at a cosmic horizon? That is the question that black holes throw at us. We are used to thinking of science as a collection of rules that apply everywhere. Gravity keeps planets in orbit, atoms hold together in stable ways, energy is conserved. But when we approach the center of a black hole, the mathematics we trust refuses to cooperate. The predictions stop being manageable and instead yield infinities. That moment is what scientists call a singularity. In ordinary terms, it's a place where our equations fail. The singularity is hidden where no observation can test it directly, yet the very idea unsettles physics because it means our frameworks are incomplete. At the core, gravity becomes overwhelming. Imagine collapsing matter squeezed smaller and smaller, density shooting upward past any scale we know. According to general relativity, this process continues without limit, creating a point of infinite curvature. But infinite density is not a physical object. It is a symptom of a theory at its limit. Relativity alone says such a thing exists. Quantum mechanics, our framework for the smallest scales, resents that answer. It does not allow infinities in the same sense. At the singularity, relativity, and quantum mechanics clash. For the first time, the cosmos asks us to reconcile two frameworks that usually succeed independent of each other. The event horizon, that outer boundary past which escape is impossible, magnifies the puzzle. From the outside, relativity provides a clean description. Time slows as you approach, light shifts to red, matter appears to freeze at the threshold. From the inside, quantum effects should still matter, because particles never truly vanish without consequence. Which takes precedence? Relativity, with its space-time curves, or quantum mechanics, with its insistence on discrete interactions? Neither gives us a complete story on its own. The horizon becomes not only a physical edge, but a conceptual testing ground. This tension gave rise to one of the boldest insights of the 20th century. The standard picture treated black holes as pure absorbers. Once something crosses the horizon, it adds to mass, but nothing comes back out. Yet calculations suggested otherwise. When you place quantum mechanics over the curved background of a black hole, strange effects emerge at the boundary. Virtual particle pairs, usually forming and annihilating unnoticed in empty space, can be separated by the horizon. One particle falls inward, the other escapes. To an observer far away, it looks like the black hole radiates energy. Think of it as bubbles forming at the surface of a simmering liquid. Most collapse instantly, leaving no sign. But at the edge of a black hole, the boundary can pluck one bubble out of the pair and set it free. The escaping particle carries energy away. Over immense timescales, that drain shrinks the black hole itself. The once eternal prison slowly evaporates. This radiation became a revolutionary concept because it turned black holes from eternal captors into temporary objects with lifespans, however long. Black holes, it seemed, could in fact die. But that announcement raised as many problems as it solved. If black holes radiate, then information embedded in the matter they consumed might be lost forever behind an evaporating horizon. Quantum theory, however, insists that information cannot be destroyed. Every particle's state should be traceable if you know enough. The apparent destruction of information creates a paradox. Does the universe violate one of quantum theory's core principles? Or is our description incomplete, waiting for a deeper framework that unites gravity and quantum mechanics? This information paradox has driven decades of debate. Some propose that information is encoded in the outgoing radiation itself, hidden in subtle correlations. Others suggest space near the horizon changes in dramatic ways, forming structures unknown to current theory. Another possibility is that space-time, as we picture it, is not fundamental at all, and that black holes reveal the deeper architecture beneath. Wherever the answer lies, the paradox keeps pressure on theorists to resolve the divide between the giant and the tiny, between continuous space-time and quantum discreteness. Nowhere else in the universe do we encounter such pure extremes. Neutron stars come close, but their matter still resists collapse by neutron degeneracy. In black holes, all ordinary forces surrender. Gravity rules without competitor. That makes black holes natural laboratories. They create conditions far beyond what machines on Earth can replicate. Colliders accelerate particles to high energies, but nowhere near the forces at an event horizon. Temperatures in stars rise into millions of degrees, but disks near black holes reach much higher. If you want to stress test the laws of physics, black holes are the place. Seen this way, they're not just monsters consuming stars. They are instruments provided by the universe itself, cosmic-scale devices that let us glimpse what happens when known rules strain to breaking point. Every observation of their behavior becomes a clue. Do they spin in predictable rates according to relativity? Does the pattern of radiation match the quantum prediction? Does the structure of their shadow corroborate both? These systems provide evidence either to support or overturn our theories in the toughest possible environment. This is why black holes sharpen science rather than break it. By forcing two dominant frameworks to confront one another, they highlight missing pieces. When an equation outputs infinity, it points to the need for a better description. When a paradox arises, it becomes a signpost to deeper order. Instead of allowing contradiction to stand, scientists treat these points as cracks in the surface, hinting at something beneath. Many expect that the resolution will be nothing less than a unified framework, combining quantum mechanics with gravity, the long-sought theory of everything. For you, what changes is perspective. The black hole that once seemed a distant curiosity now becomes a working tool for physics. Its existence compels scientists to test assumptions, to refine methods, to imagine what uncharted regimes require. Each attempt to reconcile the paradox feeds back into broader understanding. Progress in quantum gravity, in holographic descriptions, in space-time thermodynamics, all were spurred by the riddle of black holes. Without them, the path to deeper physics might have taken even longer to emerge. To appreciate the scale, imagine throwing a book into a black hole. Relativity tells you the mass increases, the horizon slightly expands, and all other details vanish irretrievably. Quantum mechanics argues that the information in that book, its particles, arrangements, states, cannot disappear into nothing. Between those two statements sits the paradox. How can both be true? The search for an answer compels theories that stretch from extra dimensions to holographic universes. Whether any of those ideas hold in the end, the quest itself reveals how fertile black holes are as theoretical engines. Remarkably, even the concept of entropy, our measure of disorder or hidden information, finds new layers here. It turns out the entropy of a black hole is proportional to the area of its horizon, not its volume. This challenges intuition. We think of information as filling a space like contents fill a box. Black holes suggest instead that information fits naturally on a surface, encoded on a two-dimensional boundary. That observation has rippled through physics, inspiring ideas that our entire universe may itself operate like information stored on a vast horizon. In practical terms, the future of this work will depend on more refined observations. Each improvement in imaging, each new gravitational wave detection becomes another lever. As we check shadows, listen to mergers, and measure evaporation indirectly, we produce data points that either reinforce or challenge existing models. The boundaries of black hole science do not remain only in mathematics. They translate into measurements. With enough accumulation, contradictions will sharpen into hints of the deeper theory hiding beneath relativity and quantum mechanics. So when you hear that black holes threaten science by breaking its laws, think again. They set the stage for science's evolution. They are barriers in one sense, but in another they form gateways, forcing us to expand our frameworks, to question boundaries we once assumed firm. An event horizon is not just the edge of visibility, it is the edge of our theories, daring us to push past. The striking truth is that instead of weakening physics, black holes strengthen it. Each paradox tested, each radical idea checked against them, either survives and grows or falls aside. Through them, science becomes sharper. They remind us that every rule we treat as universal is provisional, valid within domains, yet open to expansion when the cosmos presents harder questions. And this leads us forward. If these laboratories at the heart of collapse can tell us how space and information connect, then they may also tell us something larger. What role do these cosmic engines play in the wider architecture of galaxies themselves? Could invisible monsters actually be the architects of galaxies? At first the thought sounds backwards. Black holes are famous as destroyers, devouring stars and swallowing energy with no return. Yet when we look at the universe on the largest scales, the evidence points to the opposite. These dark centers may act not only as engines of destruction, but as shapers of the grand structures around them. To understand why, we need to trace their effects beyond a single star and consider what happens when the mass at a galaxy's heart grows to millions or billions of solar equivalents. In nearly every galaxy studied, from small spirals to giant ellipticals, astronomers find evidence of such a central giant. These are not ordinary stellar mass remnants, but supermassive black holes that dominate their neighborhoods. Their gravity rules the inner core, and their influence spreads far beyond. The paradox is this: an object that hides itself and consumes all light seems to also coordinate the growth of stars tens of thousands of light years away. Instead of serving as silent tombs, they function as regulators, balancing creation and destruction. At the center lies a simple process, feeding. When gas drifts too close, it forms a disk as it spirals inward. This disk can shine brighter than every star in the host galaxy. The energy released stirs the interstellar medium, heating surrounding gas clouds. But not all energy stays trapped near the center. Some of it launches outward in the form of jets, narrow streams of matter blasted from the poles of the black hole system. These jets extend not merely across the galactic core, but sometimes for millions of years into intergalactic space. Imagine a fire hose spraying with such intensity that it reshapes entire neighborhoods. These jets carry particles at close to light speed. As they plow into surrounding gas, they compress it, heat it, and stir shock waves. The effects ripple outward. Some regions of gas are crushed to densities high enough to spark new star formation, while others are blasted apart, preventing stars from forming at all. In this way, the jets act as regulators, turning star birth on or off across wide domains. The outcome depends on timing, orientation, and the evolving galaxy environment. Instead of random chaos, the process shows rhythm. Feeding at the center controls growth at the edges. It is useful to think of a black hole not as a vacuum cleaner, but as a thermostat. In a room, a thermostat does not create heat or cold, but it tells the system when to start or stop. Likewise, a supermassive black hole does not produce stars itself, but moderates the conditions for stellar birth. If too much gas collects, it may ignite starbursts beyond what gravity alone would support. But energy driven from the black hole heats and disperses gas, quenching that process. Through these cycles, a balance emerges. The galaxy avoids exhausting all its fuel too quickly, yet also prevents stagnation. This perspective reshapes the role of black holes. Instead of anomalies sitting useless at the center, they become integral to the life of galaxies. Their mass correlates closely with the mass of the galaxy's inner bulge, suggesting a deep link between how galaxies grow and how their central monsters evolve. As the black hole gains mass, so does the stellar structure around it. Research has shown again and again that the size of one predicts the size of the other. It is as if galaxies and their black holes develop in tandem, neither able to grow without the other. Our own Milky Way stands as a case study. At its core lies Sagittarius, a star, a black hole of several million solar masses. Most of the time it accretes matter quietly, but evidence showed occasional flares when gas clouds wander too near. Over cosmic time, these episodes release bursts of energy across the central region. The outer spiral arms form stars, planets, and, ultimately, observers like us. Without the regulation from the center, the rate of star formation might have been drastically different. Our galaxy's history is in part the record of the push and pull set by its central black hole. Think about the scale required. A star exists for millions to billions of years, shining by the fusion in its core. A black hole by itself does not shine, but the activity around it can rival or exceed entire galaxies. Jets stretch thousands of light years, heating and stirring matter far from their origin. This influence radiates not only within the galaxy, but also into intergalactic space, seeding magnetic fields and redistributing elements. What originates as matter, falling inward, becomes energy spreading outward across structures larger than any single galaxy. The history of galaxies reflects this partnership. Early in the universe, supermassive black holes fed more actively. Their jets and disks lit up as quasars, sources bright enough to be seen across billions of light years. In those youthful galaxies, bursts of energy may have determined how stars formed for generations to come. As galaxies matured, many black holes calmed, entering quieter stages where their impact was subtle rather than overwhelming. Yet the balance they created early endured. Star formation had been checked, gas reserves reshaped, and the future paths of galaxies established. One way to picture this is to imagine a gardener tending soil. Too much water, and the seedlings rot. Too little, and they fail to grow. A gardener ensures balance by adding or withholding nourishment at the right time. Supermassive black holes operate in an equivalent fashion on scales far beyond the human imagination. Their outbursts stop galaxies from producing stars too rapidly, while their energy injections also compress certain regions, encouraging growth in others. The result is a controlled balance sustaining galactic evolution. Evidence continues to mount. Observations show galaxies with active black holes tend to have altered star formation rates compared to those with quiet cores. Computer simulations that incorporate the feedback from central black holes produce galaxies more closely matching what we see in surveys. When the regulation is left out, galaxies in the models grow too fat, their stars too numerous, their structures mismatched with reality. Only when the feedback from black holes is added does the simulated universe resemble the observed one. This realization changes how we view cosmic architecture. For most of history, people assumed stars built galaxies and black holes were rare side effects. The story appears reversed. Black holes arrived early and acted as focal points, guiding the development of stellar systems around them. The galaxies we see are not despite the black holes in their centers, but because of them. Their suppressing and fueling actions determine when stars can form and when they must wait. Without these regulators, the universe would look drastically different. Our galaxy's own story gives us a personal angle. Sagittarius. A star sits quiet now compared to its ancient past, but signs of past outbursts remain. Clouds of gas near the core carry scars of heating. Radiation echoes recorded in surrounding matter suggest past flaring episodes that changed local chemistry. These traces remind us that the apparent calm is misleading. At any moment, fresh matter might clash with the event horizon, sparking another round of jets and outbursts. The Milky Way has grown in the shadow of this regulation. Even the conditions that allowed Earth to form occur within that broader framework. What does this mean for us as observers in the present? It means we inhabit galaxies not as static collections of stars, but as ecosystems with a central regulator. The feedback loop between black holes and star formation quietly set the parameters for our existence. Long before humans measured telescopes or pondered cosmology, the invisible architecture was underway. Each galaxy is shaped by its hidden giant, playing an orchestrating role across billions of years. Black holes therefore graduate from being singular oddities to becoming engine rooms of structure. Once seen only as destroyers, they are now cast as builders. They provide checks and balances. They channel energy outwards, and they determine the flow of star formation. The label monster remains true in part. They are violent and unforgiving, but another label adds itself comfortably: architect. In shaping galaxies, black holes prove they are not only consumers, but also creators of the cosmic order. From this perspective, cosmic evolution takes on a new logic. Galaxies and black holes cannot be separated in their histories. Each one guides the other, synchronizing mass and energy across scales inconceivable yet measurable. When you look up at the night sky and see a spiral of stars, you are not only seeing luminous matter, you are also seeing the invisible signature of the black hole in its center, which over billions of years has written part of the pattern you observe. This view leaves us with a natural transition. If invisible monsters can act as the architects of galaxies, regulating star birth and altering structures on scales of millions of light years, might their role stretch even deeper? The hints lead us into speculation, ideas where black holes are not only shapers of galaxies, but doorways to far stranger possibilities about the universe itself. What if black holes are not just prisons, but pathways? For most of science, their role has been described in terms of finality. Matter crosses the horizon and never returns. Time slows, gravity dominates, and everything that enters disappears into silence. Yet alongside this picture of doom and enclosure, another line of thought has persisted. Could these same objects that appear to seal reality off also open doors to somewhere else? The pull of that question does not rest on fantasy alone. Certain solutions in the mathematics of relativity permit structures that resemble tunnels, wormholes connecting distant places, or even linking different universes. The idea is simple in statement but staggering in implication. If space-time can bend and fold, then perhaps it can connect in ways that bypass distance. A wormhole, theoretically, would serve as a shortcut through the cosmic fabric. Pass through one mouth and emerge light years away, or possibly in a time earlier or later than the one you started from. The equations allow such shapes under certain conditions. The real question is whether nature herself permits them to exist, and if so, whether they could remain stable long enough for anything to pass through. Black holes become natural candidates for the mouths of such tunnels. Imagine them not only as drains through which all matter disappears, but as entrances to hidden channels. The event horizon in this picture is no longer a one-way grave, but the frame of a gateway. On the far side might be a white hole, an object that ejects matter and light instead of swallowing them, or perhaps an opening into a region not connected to our own universe. The speculation remains bold, but the thought has weight because it emerges from the same mathematics of space-time curvature that predicted black holes in the first place. The difficulty is in the details. Wormholes, in theory, require unusual forms of matter with negative energy properties to hold them open. Without such exotic stabilizers, the immense gravity around a black hole throat would crush the tunnel shut before anything could pass through. Current physics has no confirmed evidence that such matter exists. Some quantum models suggest it could under rare conditions, but so far, this remains out of reach for direct study. In practice, black hole observations give no sign of wormholes, only the more familiar accretion disks, jets, and mergers. They behave like endpoints, not doorways. Still, the fascination endures. The possibility that a black hole might also be an exit to another world fires the imagination because it links the most extreme object in the cosmos with a sense of continuation. Instead of absolute destruction, there is transformation. Even if the probability is small, the concept redefines what hidden could mean. It also reshapes how we think about beginnings. Some theorists propose that our own universe could have inflated from the core of a black hole in another universe. From the outside, to observers over there, matter fell into a horizon. From within, that collapse may have appeared to us as a big bang, the birth of a new expanding cosmos. Such speculation carries philosophical weight. If universes can sprout from black holes, then what we call the beginning might simply be a transition point inside a larger network of spacetimes. Creation is not unique, but recursive. Endpoints are not terminal, but generative. For us, seeking origin stories has always been a way to anchor meaning. Black holes as portals suggest that our origin lies inside the death throes of another world. That image overturns traditional boundaries between creation and destruction. But we must balance imagination with limits. No telescope has revealed evidence of wormholes. No detector has captured signals supporting other universes blooming from black hole cores. The mathematics allows the shapes, yet nature may never build them. What we observe, disks of gas, bursts of radiation, gravitational waves, points back to black holes as we first understood, regions of collapse, not tunnels. For all the richness of theory, astronomy deals in what can be measured. Whenever speculation rises, instruments hold it to account. The allure persists because wormholes directly speak to human questions about travel, escape, and contact. They fit into stories of instant journeys across space, of hidden back routes through an otherwise impassable terrain. You can compare them to secret shafts in the Panama Canal, unexpected shortcuts that change what a channel can do. Yet until we see physical hints, they remain at best thought experiments. The line between physical structure and science fiction is held precisely at the barrier of observation. Even without proof, the speculation remains useful. By asking whether wormholes exist, scientists test the reach of relativity, evaluate the role of quantum fields, and examine what forms of matter could stabilize space-time. The struggle sharpens science itself. Proving that such constructs cannot exist within our universe would be as meaningful as finding them. Both outcomes show us where physics draws its lines. Each scenario forces equations to extremes, revealing either flexibility or failure. The same applies to the idea that a black hole could birth a new cosmos. Observationally, we cannot peek inside a horizon to test it, but mathematically the structures can be mapped, singularities hidden from outside view by horizons and budding into new domains of time and space. These models remain speculative, yet they remind us that what begins as destruction from one perspective could appear as expansion from another. Whether real or not, they help frame our universe as part of a possible larger landscape. Philosophically, this carries heavy implications. If black holes are bridges, then the fate of everything falling into them is not final erasure, but continuity somewhere else. Our notions of death, permanence, and irreversibility become challenged not only at human scale, but at cosmic scale. Entire galaxies may feed their centers, but instead of being erased, the matter may play a role in forming another universe. The cycle becomes a labyrinth of pathways. Our fate as observers might be one branch within a maze far more complex than we can map. At the same time, one must recognize the lack of confirmation. To this day, black holes remain what we can measure them to be, regions of immense density, producing observable phenomena consistent with general relativity. The radiation, the mergers, the shadows, all match predictions for collapsed masses. No deviation so far demands we swap in wormholes or baby universes as explanations. The spectacle is enough without supposing hidden tunnels. Yet leaving the possibility open sustains creative tension in physics, urging us to pursue both theory and observation more deeply. That creative tension reflects our dual drive. We want certainty, but we also want wonder. We build instruments to press accuracy, yet we let equations lead imagination toward landscapes we may never touch. Black holes, sitting at the edge of what can be known, embody this balance. They give us confirmed facts, mass, spin, shadow sizes, but they also open doors to speculation about unseen routes through reality. We cannot yet tell if those doors are real, but the act of seeking them frames how physics progresses. For you as an observer, this means black holes remain more than engines of gravity. They are symbols of possibility. When we consider them as potential gateways, we engage both science and philosophy. Even without proof, wormholes and universe creation theories remind us that the cosmos may be built on patterns we do not yet grasp. They extend the map of what could be true, even if we never confirm them. So to return to the question, are black holes prisons, or are they pathways? The best answer today is that they are still prisons in every observation made, but they might also be pathways in equations not yet tested. The truth could lie entirely in mathematics, never manifest in reality. Or one day, an observation may force us to revise. Until then, these dark objects remain the strongest points of speculation we have, where mystery meets rigorous theory, and where the edges of knowledge blur into imagination. In that sense, black holes serve two roles at once. They anchor our physics in reality by matching predictions about gravity's extremes, and they stretch our thought into unfamiliar directions by admitting wormholes and baby universes into the conversation. They are both stabilizing checks on theory and open invitations for further invention. The paradox mirrors their nature, invisible yet blinding in influence, destructive yet fertile in possibility. Speculation aside, we must ask what lies ahead in concrete terms. If we are to move from thought experiment to evidence, we will require better tools. Next-generation telescopes, more sensitive gravitational wave detectors, and new ways of charting the sky may provide data sharp enough to test ideas at the boundary. What comes after seeing the unseeable? Humanity has already managed to expose the outline of a black hole, to hear the faint quiver of space as giants collided, and to measure the flickers of radiation from their feeding disks. But the next frontier stands ahead of us, waiting in new instruments under construction and in questions that will not go away. What comes next is not only sharper images or clearer signals, but entirely new senses added to our exploration of the cosmos. The first step lies in building better eyes. The planet-wide system that produced the first shadow of a black hole is being refined. More observatories are joining the network, increasing resolution, adding new wavelengths of observation, and aiming for the possibility of capturing movies rather than still frames. Instead of a single blurred outline, the dream is to watch matter actually move around the event horizon, to see the hot gas swirl, flicker, and fade. Motion, rather than static pictures, will reveal how a black hole feeds in real time, giving us a direct performance instead of a snapshot. At the same time, efforts are underway to extend our hearing. The first gravitational wave detectors have already confirmed collisions of stellar mass black holes, but next-generation instruments will be sensitive to lower frequencies and larger-scale mergers. With these, Entire families of supermassive black holes colliding at galactic centers could be audible across the universe. It is like upgrading from hearing a drum beat in the next room to listening to an orchestra playing across continents. Space becomes not just something we see or measure, but something we listen to in different ranges. But the most enticing prospect lies in a category of black holes we have yet to confirm, the primordial ones. These would be relics from the first fractions of a second after the universe began, formed by fluctuations of immense density trapped in gravitational wells during the earliest expansion. Unlike the black holes we know, born from stars or grown at galaxy cores, these primordial versions would trace the initial blueprint of the cosmos itself. Detecting them would be a way of studying the first instant of cosmic time. Yet they would be small, perhaps no bigger than mountains, and hidden among the vast sky. To find them requires sensitivity beyond anything we have yet built. Why does this matter? Because if primordial black holes do exist, they may answer the riddle of dark matter. The galaxies we observe rotate too fast to be explained only by visible stars and gas. Some invisible weight holds them together. For decades, physicists have hunted exotic particles to explain this unseen matter. But what if the missing mass is not particles at all, but swarms of tiny black holes formed at the dawn of time? Finding even a handful of them would turn a cosmic puzzle into an extraordinary result. This is where the link between astronomy and fundamental physics becomes tightest. Every new tool built for black holes doubles as a probe into the deepest laws of nature. Improved imaging tests, relativity at the edge of collapse. Gravitational wave detectors reveal whether space-time ripples exactly as predicted or if new effects show through. Searches for primordial black holes could decide whether dark matter is particulate or compact objects. In each case, the stakes climb beyond astronomy, reaching into the foundations of physics itself. Projects under construction promise to push this forward. New space-based detectors will stretch their arms millions of kilometers apart, waiting to measure gravitational waves in bands unreachable from the Earth's surface. Expanded networks of telescopes will trace not only radio waves, but higher energy bands at unprecedented clarity, watching disks flare and jets retreat. Computer models paired with these observations will simulate entire life cycles of black holes. Instead of isolated glimpses, we could produce continuous maps of how black holes are born, how they grow, how they flare, and how they die across cosmic time. This pursuit requires enormous patience. Every instrument must filter signal from noise, measure at scales of absurd precision, and coordinate across nations. But the payoff could equal or even surpass the emotional impact of the first photograph. Seeing matter flow across the event horizon in moving pictures, hearing the vibrations of supermassive mergers, and finding traces of black holes from the first split second of time. Each step would redefine what we mean by knowing. They are not speculative dreams, but concrete possibilities in the next generation of science. The idea of mapping black hole life cycles is not trivial. Right now, our knowledge is piecemeal. Stellar mass black holes born from collapsing stars, intermediate candidates only tentatively noted, supermassive giants confirmed but with uncertain origin stories. With new tools, we may trace the entire chain from birth to feeding, from quiet dormancy to violent merger, and finally to evaporation across unimaginable timescales. A complete map would unify astronomy, much like a periodic table unified chemistry, scattered cases drawn into one coherent framework. For you, the significance of this is scale. Each new tool widens the set of senses humanity possesses. We began with bare eyes on the night sky. We extended our vision with telescopes. Then we built instruments that could hear signals beyond light. Now we stand ready to add clear movies, low-frequency ripples, and perhaps even indirect signs of cosmic relics. It is not a matter of replacing one method with another, but of layering perception. With every sense added, the cosmos stands in greater detail, like a picture coming into focus as more pixels fill the screen. One could imagine the universe itself as a complex symphony. For centuries, we had only one instrument to hear it, the visual light that reached our eyes. Black holes forced us to tune in other instruments: radio, X-ray, gravitational waves. The next frontier is to hear both the deepest bass lines, produced by massive mergers at galactic centers, and the highest notes, provided by faint bursts from primordial seeds. The more instruments tuned, the more complete the song becomes. Each detector adds another line of melody until the full structure of the universe's composition can be heard. There is a larger dream here. Black holes are not only objects of curiosity. They may be the keys to unifying physics. They pull relativity and quantum mechanics into confrontation at their cores. They capture matter and information in paradoxical ways. They tie galactic formation to cosmology. They may even carry the fingerprints of dark matter within them. By expanding our senses, we are not doing astronomy alone. We are pushing physics toward its deepest answers. In that way, the next tools are not only telescopes or detectors, they are steps on the path to the oldest questions. What is matter? What is space? Why is there something rather than nothing? We stand in a curious position. The first image of a black hole's shadow drew headlines around the world. The first chirp of gravitational waves reshaped our view of the cosmos. Yet those may be only the opening notes in a symphony that has barely begun. The coming decades promise equally historic breakthroughs, achievements that will sit beside those firsts in the story of exploration. The trick is to wait, to build, and to persist with patience as black holes slowly give up their secrets. It is helpful to imagine where our knowledge is headed. Today we can name and measure specific black holes, follow the paths of stars around them, and capture radiation from their disks. Soon we may know their family tree, their growth history, their hidden role in cosmic structure, and their ultimate fate. The promise is not that we will find answers to every riddle, but that each answer will change the questions. The line between astronomy and physics will blur until they are aspects of the same search, uncovering how matter, energy, and space interact at extremes. In that sense, our species is on the edge of discoveries as dramatic as the first image. The next frontier offers the possibility to connect microphysics, particles, quantum states, dark matter, with macrophysics, galaxies, cosmic expansion, space-time. Black holes sit at the seam between the two. As long as we keep constructing better tools, we will keep pulling threads from their mysteries. Each thread leads not to a loose end, but to a fabric we can now start to piece together. And there lies the quiet truth of the frontier. These instruments are not only mechanical constructions. They extend our presence into aspects of the universe that were once impossible to imagine. From the edge of collapse to the dawn of time, they trace events that shape everything we see. The next breakthroughs, whether motion pictures of horizons or detection of cosmic leftovers from the first instant, will not simply add lines to textbooks. Black holes began as unseeable ghosts, whispered only in equations. Today they guide science forward, turning from imagined shadows into measured facts. We can trace their pull on stars, record their radiation, hear their mergers, and even capture their silhouettes. They remind us the universe hides its secrets well, yet offers clues for those patient enough to look closely. Each new method, sight, sound, or signal, uncovers another layer of truth. Perhaps the most unsettling thought is also the simplest. The origin and destiny of everything we know may lie hidden beyond that horizon where light itself cannot return.